So today we are going to continue working in section 3.2, and we're going to focus on finding the domain of a logarithmic function. I'm going to try the notes a little different today. Mine are all written out, and I'm just going to try to walk through them for you. Again, if you are someone that feels like it's useful to write down all the notes on your own, you can either copy these offline and see if you can follow through as I go. You can pause the video at any time at the different steps. Okay, so just keep that in mind as we go. So again, we are going to be working on finding the domain of a logarithmic function. So what is important about this? The main point is the argument. The input of the logarithm must be positive. It must be greater than 0. So for each of the next examples, we want to find the domain of the function. So my first function is a. My example is a, so f of x equals log base 4 of x plus 3. So my argument here is everything in the parentheses, okay? So my argument here is x plus 3. And I need that argument, I need that input to be positive because that's in the definition of a logarithmic function, okay? The argument must be positive. So I am just going to set up the inequality x plus 3 is greater than 0. And I'm going to find the solution to this set, and that's to this inequality, and that's going to be my domain. So I'm just going to subtract 3 from both sides. I end up with the inequality x is greater than negative 3. So my domain is going to be negative 3 to infinity. If you have a question about where that comes from, think about your number line that would be the solution for x is greater than negative 3. Negative 3 would be your key number. Because the inequality symbol is greater than, we're going to have an open circle. And we are going to shade everything to the right because we're looking for all numbers that are greater than negative 3. Okay, that corresponds to the interval negative 3 to infinity. Okay, open parentheses at both sides. So our next example is f of x equals the natural log of the argument 3 minus x. So again, the base doesn't matter, okay? The log symbols don't matter. All we're looking for when we're finding the domain is to have, it's important that our argument is greater than 0. So again, we are setting our argument greater than 0 and solving. So just like above, we're going to start by subtracting 3 from both sides. It's really important. Sorry, I'm going to scoot this a little bit. It's really important that you don't forget this negative sign. Okay? And this is the step that I feel like people might forget. Remember to change the inequality when you divide by a negative. So to get x by itself, we need to divide both sides by negative 1. And when we do that, we need to remember to change our inequality symbol from greater than to less than. The last time I taught it, students wanted to be reminded or know for the first time why you flip when you divide a negative. I want you to think about something like this. I think everyone agrees with me that negative 2 is less than 4, right? Because negative 2 is to the left of 4 on the number line. But let's divide both sides by negative 1. Okay, we get 2 and we get negative 4. Is 2 still less than negative 4? No, 2 is greater than negative 4. Okay, so anytime that you multiply or divide by a negative, you need to change the inequality to make sure that you're keeping a true statement. Okay, so that's what I did here. I had negative x. I needed to divide by negative 1 on both sides. I got x is less than 3, so my domain is going to be negative infinity to 3. Again, if you are not ready to go right to your interval notation, you're thinking about this inequality. So 3 is my key number. I have an open circle there, and I'm looking for all numbers less than 3. Okay, and that will correspond to the interval -infinity to 3. Okay, let's go to our next one. Okay, our next one, I have f of x equals the natural log of the quantity x minus 3 squared. So we are looking for our argument, x minus 3 quantity squared, to be greater than 0. I'm sorry, this is a typo. Oh, it's not a typo. I'm sorry. You need to think this value, x minus 3 quantity squared, is greater than or equal to 0 for all x. Okay, because anything squared is going to be a positive value. If you take 5 and square it, you're going to get 25. That's positive. If you take -5 and square it, you're going to get positive 25. Okay, so whatever is in the middle, we square it, we're going to get a positive value. So we only need to worry about when x minus 3 is equal to 0. Okay, because our argument cannot be 0. So we are just going to solve the equation x minus 3 equals 0. We add 3 to both sides, and we're going to get x equals 3. So our domain is, I think we've done this notation before, the curly Q braces mean set, so it's a real number such that x is not 3. Okay, and the way that we do this in interval notation is we go from -infinity to 3 and 3 to infinity. Okay, for D, how this one is a little different. Notice that this time we have an odd exponent. So we have the natural log of x minus 4 to the 17th. If we have a positive number to the 17th, this will be positive. However, if we have a negative number, say this simplified to -1, -1 to the 17th is still going to be -1. So if there's an odd exponent, we need to worry about the whole argument being greater than 0. So I need to look that x minus 4 is greater than 0. So hopefully you can see this simplifies to x is greater than 4. Okay, so our domain is going to be x is an element of the real numbers. This E means element of, and all this means is x is a real number. Our line means such that x is greater than 4. Okay, so this is another way to represent our domain. Our next one, excuse me. Okay, we have the natural log of x minus 4 to the 100th. So our factor is the same as in D, except for this time we have an even exponent. Again, we talked about even and odd exponents before. If it's an even exponent, this expression raised to an even exponent is going to be positive, it's going to be non-negative, right? So the only time we have to worry about it is we have to worry about this factor x minus 4 when it's equal to 0. Okay, so I am going to set x minus 4 equal to 0, which simplifies to x equals 4. X equals 4 is the number that I have a problem with, because if I do 4 minus 4, I get 0. 0 raised to the 100th is 0, and I cannot take the natural log of 0. My argument has to be greater than 0. So my domain is x is a real number such that x is not equal to 4. Okay, so important here, if you have an odd exponent, you're setting your factor greater than 0. If you have an even exponent, you're setting your factor equal to 0, and you are excluding the value that you get in your equation. All right, last example. I'm hoping this one can be under 15 minutes today. Okay, so same process, but we have something that's much more complicated. Okay, so I am looking at f of x equals log base 3 of the quantity x squared minus 8x plus 15. Notice that this is the same equivalent expression to log base 3. I'm going to factor my x squared minus 8x plus 15. I'm looking for two numbers that multiply to 15 and add to negative 8. I got my two numbers as negative 3 and negative 5. Okay, so I was able to factor this to x minus 3 times x minus 5. So our argument, okay, our input needs to be greater than 0. Okay, and so the next thing that I'm going to think about, this is now solving a quadratic inequality. This should be familiar to you as an Algebra 2 topic. If it's not, you need to go back and look at solving quadratic inequalities. Okay, so the first thing that I need to do is I need to think, when is this equal to 0? And it's going to be equal to 0 when x equals 3 or when x equals 5. So my next step is going to be to plot these numbers to define my intervals. Okay, so I drew a number line. I plotted 3 and I plotted 5. I know that those are open circles because they're going to make this inequality equal to 0, so they're not going to be included in the solution. And the next thing I'm going to do, I'm going to notice that this breaks my number line into 3 different intervals. So I'm going to pick test numbers in each interval. I always pick 0 whenever I can. It makes my arithmetic easier. Between 3 and 5, I could pick any number. The easiest number I think to pick is an integer 4. And above 5, again, you could pick 100, you could pick 1,000,000. Okay, I'm picking 6 because it makes my arithmetic easy. So after that, I am going to check my test number. So I'm checking 0. I am putting 0 in for x, okay? So in both places, I put in 0. I have 0 minus 3 times 0 minus 5. I want to see if that's greater than 0. These numbers are pretty easy. I could do this out, right? Negative 3 times negative 5 is 15. That's greater than 0. You can also just think about the sign. 0 minus 3 is going to be a negative. 0 minus 5 is also going to be a negative. A negative times a negative is going to be positive, which is greater than 0. So my interval below 3 will work. Okay, similarly, if I check x is 4, I'm going to have 4 minus 3, that's a positive. 4 minus 5, that's a negative. A positive times a negative is going to be a negative, which is not greater than 0. So my interval between 3 and 5 is not going to be part of my solution set. I'm running out of time, so I just want to show real quick. If you check 6, you're going to get a positive times a positive, which is going to be greater than 0. So my solution set, I have all numbers less than 3 and all numbers greater than 5. So my domain is from negative infinity to 3 and from 5 to infinity. Okay, I feel like this last part was a little rushed, but I'm hoping that it's familiar from Algebra 2. If it's not, please let me know, and I can put up another example. Have a good day, and please check in with me if you have any questions.